Hey everyone, so I hope everybody can hear me fine. I'm sorry for not being in Prague with you. I wish I could have, but unfortunately it was not possible this year. Today I'm here to talk about Grout, which is a DPDK hosted project since last September. Um, Before before starting this, this is me. I work at Red Hat in the OpenStack and NFV integrations team. Um, and Here's the agenda for today. So for those who missed the talk in September, I will give you a summary of what is Grout, and then we'll give more insights about where the project is today, and then we'll dive into some highlights of how it's built and some of the new features. I'll try to give you a short demo and uh, try to see where we're going with that project. Um, so for anybody who missed the talk we gave with David last year, I'll put some links here. Hopefully the slides will be uploaded on the talk later on today. So what is Grout precisely? So initially we wanted to have a vendor independent software router. So we want something to be able to replicate whatever VNF or CNF that we need to run in OpenStack or OpenShift. We want to have something generic, which isn't tied to any specific vendor. We wanted that project to be strongly tied with DPDK, and we wanted so it could be used as a I don't want to say flagship project, but something to bring more visibility for DPDK libraries and drivers. And also, we made absolutely zero compromise on the design of the stack. So it means, I will explain that later on, but it means that Grout, the graph, the packet graph is really strict with what nodes are allowed to handle based on the stack level where we are in the stack. I will explain that later on. It has a way to, so you have a API with a Unix socket where you can exchange messages in order to program and configure Grout. Obviously, it's completely open source. There's no, it's open source, right? And as I said, it's a hosted project. Where did we start last year? So in September, we had V4 and V6 IP forwarding, multiple VRS. We had some VLAN support and a proof of concept for IP in IP V4 tunnels. Since then, we have made significant progress on multiple fronts. So since February, I think, you can actually DNF install Grout on Fedora. We added a bunch of debugging tools in order to trace packets, and also you can enable packet logging dynamically. You can dynamically move the data path threads from one CPU to another without restarting or anything. We have a way for packets entering DPDK interfaces to be sent to Linux. For example, if you want to have strong SWAN or FRR integration, you can actually have inline BGP traffic terminating on BGPD, but the packets will go out DPDK port controlled by Grout. We also added the L1 cross-connect mode, which is similar to test PMD in IO mode. We added that because at Red Hat, we have internal tests where people were using test PMD, and we try to make them move to Grout. And since the L1 cross-connect is exactly the same as test PMD IO mode, it was simpler to start with that and then move to IP forwarding. And also we got the segment routing based on IPv6 added by an external contributor this year, which is quite exciting. So where are we going? So right now there's a FR backend plugin which is in progress. It should be probably ready at the end of this summer, I think. We'll also be working soon on a stateless NAT node. So we'll start with DNAT, and maybe we'll do source NAT, and so that will involve connection tracking at some point. And also I wanted to highlight some of that graph pipeline mode for slow path handling. Maybe this is something we can talk about during the Q&A at the end. I would like to challenge the guys at Marvel about how we could go with this. The idea would be to have packets being handed to other CPUs for slow path handling. So for example, when you receive an ARP reply or request, instead of processing that in the data path, you would want to send that to another CPU so that you can continue processing other packets at high speed and let the control plane CPUs handle that. But so for now in Grout, we kind of need to send the packet out the graph to be handled differently, and then it needs to re-enter at some point. So we would like to have something more integrated, and so everything stays in the graph. Let's go on. I'll give you an overview of how the packet flow is handled in Grout and how we manage the network layer separation between nodes. Also, we'll see how the graph looks like today, and we will have some quick look on the new features that are landed recently. So this is basically a simplified view of the IPv4 graph. So what happens is that we have layer 1 RX node, which iterates over every port plus QID that we have. And it will resolve which interface, logical interface, is associated with that port number. It will then send the packet to Ethernet input, since now we only handle Ethernet. And the Ethernet node will pop the Ethernet header, possibly the VLAN as well. And it will send the packet to IP if the Ethernet prototype is IPv4. Otherwise, it will send it to another node. This is done dynamically without jumping back to the previous talk, we started this work before feature arc was introduced, and we found other ways to dynamically register nodes based on another mechanism. Maybe that's too technical dive for today, but maybe we can talk about later. So in IP input, now we have shifted the mbuf offset to the layer 3, and we can do a route lookup based on the receiving interface. which gives us a next hop. And then while at layer 3, we can do TTL decrementation and recalculate the checksum. And then based on the next hop we got in route lookup, we can determine where we need to send the packet. And then, so at that point, we can push a new Ethernet header with the correct destination and source. We can push back the IPv4 Ethernet Ether type and then transmit the packet on the correct port. Right. So this was in September, the graph with the highlighted path in yellow, like this. So it was pretty simple. I have excluded all the error nodes. So this is the simplified view. So, and this is today where we are. So it's a bit more significant. At some point, we will need to stop displaying these graphs, but because I think it will become too complicated. But anyway, so as you can see, there's a lot more control operations happening. And this is what I was referring to when I talked about pipeline mode. So everything that needs to be handled by the control path is sent to control output. And then when the control plane wants to inject packets, it needs to inject them in control input. So ideally, we would need to have a better integration with the control plane CPUs or workers. But for now, we deal with that differently. So yeah, so this is one new feature. We can be handy when you're trying to debug where the packets is being dropped and why. So every node has a way to attach tracing data. So it's basically just a byte buffer that you can pass. And it's stored per mbuff. You have some sort of linked list of tracing data. And when the packets is transmitted or dropped, the tracing information will be stored somewhere in the ring. And then via the API, you can access all this traced information. So I've displayed a short example below where you can see the packet entered port 1, Q0. Then the Ethernet input node added the Ethernet header information. Then in IP input, we saw something about the external IP addresses. And then we see that the IP protocols was IP in IP tunnel. So the packet went through IP input, and it actually popped a tunnel. And then the packet was re-injected into IP input with a different IP address. And then the packet was forwarded and then transmitted to port 0, Q0, right? So you can have that, and you have the CPU ID where the packet was handled with the timestamp. Also, we added the loopback interfaces. So we have that per VRF, and it allows to send and receive packets from Linux into Grout. So it's pretty handy if you want to do inline, for example, routing protocols, or if we would like to implement IPsec, IKEY v2 in the future, we could use that mechanism. So for now, it's a bit early to make a demonstration of that, but it's used by the FR plugin, which is under development. Also, we had the L1 cross-connect mode, which I talked about earlier. So it's just a matter of setting the mode to cross-connect, and then you give a peer port, and it will act as a software wire, like TestPMD and IO mode, which is the default mode, I think. All right, so time for demonstration. So let me just switch to my terminal here. So what do I have? So I have a platform where I have a bunch of 25 gig interfaces here. And I have these two ports which have been bound to VFI OPCI. They are ready. We have 1 gig huge pages and CPUs which are isolated. So as you can see, we can use CPUs 10 to 19 and 30 to 39. Right, so what I will start with is I will install Grout first. And then I will start it. So it's just a matter of starting a systemd service like this. So it's started, and if so, we don't have any 2 meg huge pages, which is fine. First of all, what I will do is that you have a CLI like this, where you can have either interactive shell, or you can use it like a shell, like bash command or whatever, and you have interactive completion like this. So first of all, what I'll do is I will change the affinity of the data path CPUs to 10 and 30. I only need 2 CPUs, which will be fine, like this. And then I will configure interfaces. So it will be ports. So the first port P0, the args, then also displays all the drivers or PCI IDs that are available like this. And I will create a second port like this. And now show interface. We can see we have P0 and P1, and GR loop 0 was created automatically. We have one loopback, which is per VRF. So since we only have one VRF at the moment, we only have one loop interface. So now I will have a look at the topology we saw in the previous slide. So we have one north machine, which is configured with that IP address and a default route through 254. And the south machine is the same thing, but with 200 as in the IP address. So what I'll do is that I will configure, so add IP address 172.16.100.254 on P0, and on P1 I will have 200 like this. As you can see, we have our local interfaces like this, and we don't know anything about these two machines here. So since Grout has a real IP stack with all the IPv4 and IPv6 dynamic address resolution, we can directly do ping. We can ping Grout directly, so 172.16.100.254, and Grout will reply, right? So now we can see that Grout has discovered a new next hop, and it has been created 4 seconds ago. And we can also ping the other side, like we want to ping the south machine here, and it will work as well. So what happens in that case is that Grout will receive the packet and then resolve the other side of the wire and then forward the packets. So we can do a quick set trace all. So this will enable packet tracing, as I explained earlier. And now we can ping again, and we can do show trace one. Oh, wrong packet. Yeah. So in this case, we saw that so the first packet that was dropped here was a LLDP packet sent from the switch, so we don't care. But so this one was forwarded by Grout, and we can see. So there's no ARP resolution here because the next hop was still valid. But if any ARP resolution was required, you would see the ARP packets, request, reply, everything will be present in that side. And then we can also have a look at software statistics, for example. So show stats software. And every node here is a node in the global graph, and it will, so you will see the number of times that node was visited, the number of packets processed in total, and then a bunch of extra stats here. So obviously, cycles per packets here don't mean much because we're not sending traffic at high rates or anything. But you could use that to do hotspot pinpointing, like this node is taking a lot of cycles. Maybe we should have a look at that node process function. Maybe something is off, or I don't know. You can also see the hardware stats, which is using the RT-Xstats API. Right. So I think we're good for that demonstration. Let me go back here. So before wrapping up, we had significant contributions from other companies, which is very exciting because until now we were just 2 people working on the project. Now we are 3 or 4 people, which is nice. So if you are interested, please give Grout a try and give us some feedback. It would mean a lot and it will help. And also, if you have any idea of how you would like to use Grout, what would you do with it, please send us a message either on Slack, via email, or open a ticket on GitHub. That would help a lot. All right. So I think I'm done. So if you have any questions or anything, happy to answer.
Simple question. Are these graph nodes RFC compliant? Do they
Yes.
support all the must and should requirements?
Most of them, yes. So the IPv4 and v6 forwarding stack are following the RFCs. Obviously, it's not 100% complete. So some cases are not supported. But the things that we support are RFC compliant.
Compliant, so that they are production worthy. Yeah. And I'm assuming the stats will also go the same way. All the MIB counters will be supported.
So for now, we don't have SNMP compliant MIB counters, but we could provide that at some point if needed. I don't know if that's present in any RFC, by the way, the statistics.
The MIB counters are defined by RFC.
Okay. So maybe we could provide something like that, but maybe that wouldn't be done by Grout itself. That would need to be some kind of external thing that takes Grout stats and converts them to a MIB. I don't know. Sure.
Super. Thanks, Ron.
to